But this study actually involves a lot of different partners. I mentioned Antioch University. Of course, Minnehaha Creek Watershed District is involved, as well as the University of Minnesota. Tricia Moore, where's Tricia? Tricia Moore has been doing a lot of the modeling work on this study, so she's working with John Gulliver's lab. And then also we have Syntectic International, Lakeland Stack. He's does a lot of the precipitation modeling for this project. He's in Portland, Oregon, and was not able to come tonight. And then we also have our two study sites, which you'll hear more about today, the city of Minneapolis, and then also the city of Victoria, one being a built-out community, one being a growing community. And then Stratus Consulting is also providing some input. Is anybody familiar with the National Climate Assessment Report that was just put out? It's in draft form, and they are looking for comments. You can find it on the website. And I have not read all 1,100 pages of it, but I'm going to synthesize it really quick. As you can probably, as you know, it's cold outside, but our climate is warming. This information here, these are temperature projections based on different emission scenarios. You'll hear a little bit about that later. That plays into the precipitation modeling that we've been doing. I should say that Michael and Tricia have been doing. And as you can see, over time, projected in the future, we have potential severe shifts in our temperature. And I think I don't need to go into more detail than that, but we are getting warmer. And that's affecting precipitation, and that's really what we're focusing on right here today. And as you can see, this is the observed U.S. precipitation change. This is an annual precipitation, and all of this information is in that climate assessment report. It's a very well done report. The last time it was put out was in 2009. This is the update to that. It involves over 60 individuals from different agencies all over the country. And it's really a wealth of information, focuses specifically on water resources. It has a whole section on adaptation, which is why we're here tonight. In fact, Joel Smith with Stratus Consulting is one of the lead authors on that section. He's providing oversight on this project as well. But as you can see, precipitation, the dark green, that's where precipitation overall is increasing. As you can see, Minnesota's right here. This is the Midwest region. Also in New England, it's increasing as well. So that's just kind of a general picture. If we think about heavy precipitation events, extreme events, this is called the weather extreme trends study because we're focusing on those extreme big events. If you look at information that was provided, this Carl et al. In 2009, you can see there's an expected shift or increase that we're seeing in precipitation, heavy precipitation. That's the top 1% of big storms. So our rainfall is increasing and it's coming in more intense storms, and that's sort of what I want you to leave you with. If you look at the updated version of this graph, which is in that assessment report, it's expected to be even more increase, so 45% increase in very heavy precipitation events. And so what that means is, I just want to give some examples. The storm of the century, July 1987, I just had graduated from high school. I remember this clearly, 10 inches in about 8 hours in Minneapolis. The carpet in our basement was completely floating. I can never forget it. And as you may all remember, if you were here, that was a significant event in the Twin Cities metropolitan area. Total damage, $30 million or so. That was back in '87. Poca in the southwest Minnesota area had about 15.1 inches in 24 hours. That was the state record, which I believe still stands for a 24-hour period. And it had about $27 million in property damage, a lot of crop damage, and as you can see, there were some significant problems with infrastructure due to that storm. So that was another example of an extreme event. Duluth, Minnesota, we all are familiar with that. Up north, this was June of 2012, last year, 9 to 14 inches in 24 hours, depending on where you're at, and about $108 million worth of damage that they're dealing with right now. And they're having to deal with the damage, they're having to think about how they're going to repair that damage and what they're going to look like in the future. So that's something that they're struggling with right now. So that leads us to our study. Where does this study kind of fit in? And we're focusing specifically on adaptation versus mitigation. Mitigation addresses how do we reduce global warming. but this is actually focusing on what can we do with the changes that we're seeing, and how do we make our communities more resilient to changes in the future. So this is also out of the climate assessment report. This is what they outline as the adaptation process, how communities can think about what they need to do to make themselves resilient. And I can start with identifying risks and vulnerabilities. That is the technical piece of this study, and this is what we're going to present on tonight. So it's actually looking at taking precipitation projections into the future. It's looking at land use changes and how that affects land cover, and how impervious surfaces can compound the effects of extreme rain events. And then also using EPA SWIM models to model the stormwater infrastructure systems in our two study areas. So I mentioned Minneapolis and Victoria. And so the modeling assesses the risks that those communities may face in different projected precipitation scenarios. So you're going to hear more about that tonight. So that is one piece of this study. Another piece is adaptation options and costs. And that involves kind of the planning, assessing, selecting options that communities can think about. So identifying adaptation options is a part of this study, which we'll talk about tonight. Low impact development, where does that fit into managing stormwater, and can it be used as a tool to mitigate future impacts from flooding? And then cost analysis. Communities always want to know, what's it going to cost to upgrade? What's our risk in the future? So that's a part of this study too that you'll hear a little bit about as well. And then after you have that information and go through that process, then communities can begin to think about how can they implement different strategies to increase their resilience to change. And so this is the second work group session that we've hosted. The first work group session was really was charged with identifying kind of priority areas. And we also had a forum. Who was at this forum in May of 2012? You were there? Some of you were there? Okay. We also had some breakout sessions at that forum as well to identify different priority topics. And 4 key areas came out of that, and this is what you see at your tables. The 4 key areas that were identified as needing to be addressed for adaptation. Planning was education and communications, infrastructure, stormwater infrastructure, planning and land use policies, and how we can look at those to help our communities. And then also funding mechanisms. How do we pay for some of these adaptation options? So that came directly out of the first work group session that we had. So this is the second work group session, and what you're charged with tonight, after you hear some of the technical results, is to actually identify some strategies, some concrete strategies that communities can implement, can focus on and implement to increase their resilience to future climate change issues, or actually I should say climate change issues right now, as well as the future. So that's what we're going to do. And I think with that, does anybody have any questions? This is just kind of a brief overview.
I'm trying to figure, is this just generic, or is this Minnesota specific?
It's Minnesota specific. All of the technical work and the modeling is downscaled to our specific area and within our watershed, actually. So we're actually looking at very specific, from Minnehaha Creek up to the regional scale.
Because it seems like a lot of watershed districts are already doing some of this, or cities. I mean, so I was just trying to do that.
Okay. Anybody else have any questions? John?
Also, another question might be related to drought. You talked about the bigger rain events, but also if we have less frequent rain events, that could also pose problems with, foundation settling and all, keeping plants alive. So does this also address the issue of drought too?
Well, I'll let Michael maybe address that. I guess my thought is that we're dealing primarily with infrastructure and modeling the conveyance systems. So it's the large rains that, whether a system is able to convey that or not, really impacts the flooding potential. So not specifically drought. I don't think I have anything to add to that.
Well, when we look at the soil moisture for our modeling, we just took sort of the middle of the road. We didn't take very dry soils, nor did we take saturated or frozen soils. So what we're doing here as far as runoff is sort of looking at what's called antecedent conditions type 2, which is basically normal soil moisture.
Okay. Any other questions?
Let's say I probably should know this, but when you talk about stormwater infrastructure, you talk about conveyance, you're talking more than just storm sewers. You're talking creeks and everything.
Right, ponds, yeah. And that becomes more important in like a community like Victoria, which has more open space and ponds versus Minneapolis. That's the benefit of having two communities we're focusing on.
But
having those
it's
different types
natural,
of systems.
it's natural as well as man-made
Right.
conveyances.
So are we talking about building capacity on land as opposed to just pipes? Oh, because the way this reads, okay.
Oh, yeah. All right, any other questions? Okay, well, I'm gonna turn it over to Michael, and he'll talk about the technical information, and then we'll get into our work groups.
Hi.
Hi.
I apologize for people who have heard me twice before. I have to repeat some things because there is sort of some new crowds here, so I'm going to go over some sort of preliminary concepts and then sort of give you sort of where we are in our research. We're just wrapping up what we call the technical aspects of this. Is really looking at climate change, downscaling it to the micro watershed here. And also looking at the runoff model and the impacts to that runoff model as far as infrastructure and flooding. We're just starting, because that just is finalizing, then we're just starting to get into a cost analysis. So I have some preliminary cost figures for you, which are going to be updated and revised. But I thought I'd give you sort of an idea of some cost related costs. Now I know people have been here seeing this, but just to give you, this is sort of this sort of conceptual structure of the project, where we're taking climate data, both historic and global circulation models. We're looking at scenarios, so we're coming up with a lot of possibilities into the future, not just one, and basically how does the watershed respond to those differences into the future. To do that, we have to look at the current land use characteristics as far as impacting runoff specifically, and primarily we're really talking about cover type and soil type as the two drivers behind runoff. Then we are doing, especially in Victoria, looking at sort of what's projected land use going to be. So we did a build-out analysis there, and then based on the piping configuration, we basically go into a runoff model, which basically comes up with peak flows based on projected precipitation amounts, and then we can determine which of those components are adequate, and if they're not adequate, what would be the proper sizing for them to make them adequate. We are starting an analysis of low impact development on our analysis, so as we build out or look at a build-out infrastructure, what the impact of low impact development might be on mitigating some of the impact. And then finally, we're doing cost impact. So that's sort of the conceptual part, and that's why there's so many logos up on that page, because no one person can do it all. And so it's been a pleasure to work with everyone on this project. It's been a lot of fun. Again, this is just a repeat, but this is just a conceptual piece. I'm going to talk about this, but when we talk about probability and uncertainty and risk, we sort of look at the storms and the amount of rain that comes to the specific storm. So if you look at this first column, these are just storm events, historical storm events for one of the climate stations. And what we talk about is the percentage in any one year for that amount of rain to show up. Okay, and that's what that second column is. So when we talk about 2.5 inches in this data, it means that in any one year we have a 100% chance of getting at least that storm amount. Okay, as you go down, okay, let's say to 6 inches, okay, based on historical data, you know, you have a 1% chance in any 1 year to have it. And if you know probability, you know, like flipping a coin, you know, if you got a 6-inch storm this year, you're going to get a 6-inch storm next year. I mean, that's probability. Okay, it doesn't mean that once you've had it, it's not coming back for 100 years. But we do talk about these as return periods. So 100% chance, we call that a 1-year storm. And a 1% chance in any 1 year, we call that a 100-year storm. And I think you all know about 100-year floodplains. 100-year floodplains means that there's a 1% chance for a flood to raise to that level. So we use that also in precipitation when we do these analyses. Okay. Oh, sorry. And what we really are focusing on is this number right here, historically, because 10%, okay, probability or a 10-year storm is the design for most of the infrastructure that we're looking at, okay, especially in Minneapolis. And so as such, this is the storm that they size things for. And obviously some of the pipes are much older than this, so some of the pipes might not even be designed to this storm level, but this is what we're focusing on, is the 10-year storm, which has a 10% chance of returning in any 1 year. Now, we did a lot of what we call downscaling, taking global circulation models that we get from researchers from around the world, and looked at all those models to see, looked at the models we thought were probably the best models that are out there. And this is what the UN uses when they come up with their reports. This is what the US government uses when they come up with a report, but we basically use the raw data ourselves to create this downscaling. And as such, we basically came up with a whole series of rainfall amounts, and these are percentages over the historic rainfall amounts of the 10-year storm. And then scientists, engineers like one number. They want a number in which they can design things with, but scientists look at a population in numbers, and so we statistically look at a whole population, and thus, in our population, these amount of rainfalls could occur, okay, just as likely as what we call the most likely or the mean of the range. Okay, and so even though they sort of cluster here around the mean, because of the statistics, these are within the 95% confidence interval. That's what the scientists call it. And so we have to consider these as possibilities, these larger amounts.
Is that whole slide the 10-year?
Those are all 10-year, yep, for all those different models. Thank you, Lois. So really what we're doing is we decided to look at those numbers, and we really are focusing down on these numbers right here for the 10-year, and we're just calling them mid-21st century. Our projections for climate modeling, we're projecting to the mid-century up to about 2075 of when these would occur. And so the 10-year storm, this is what we get sort of for recent amounts. This is what we call our optimistic, our moderate, and our pessimistic amounts. Again, we're not saying one of these things are going to occur, but we wanted to look at this range. Just to give you an idea, that's about a 9% increase over the current, the 4.19. That's about a 32% increase, and that's about a 162% increase. Now, just to give you a concept, this is basically the Duluth storm that just occurred, and Leslie was talking about the historic storms that were hitting. And so this was just data from these climate data stations that are here, just to give you an idea of the amounts that came in that storm. And these are our climate models, okay, all these colored dots, but we threw in some of the storms that hit around this area. This is the 1987 storm, and this is precipitation depth, that is how much rain fell, and this is the percent of components undersized, that is how many of the infrastructure, how many of the pipes by linear foot are undersized. They're just too small to pass this amount of rain. And so basically, as we look at different models, you can go to any model, or you can even go to these storms and apply those numbers and get a percentage of the infrastructure that we feel is going to be challenged, and as a result going to create flooding. Either the pipes are going to fill up, we call that surcharging, or they're going to fill up and back up on the street, and you're going to get street flooding. And at the higher levels, they're going to fill up, get on the street, and go over the curbs, okay, and then get onto people's property. Okay, so that's one of the things we're looking at. So this is in Hiawatha. This is the part of Minneapolis we were studying. This is basically just to show you these maps. These are what are called stoplight maps. And so the light green, okay, right here, for example, is basically the pipes are fine and there's no surcharging. That is, they're not filled up completely. Yellow's where it starts to turn yellow, okay, is basically where the pipes are filled up, but they're still flowing and the water hasn't backed up on the streets. The blue is basically street flooding. And so in a sense, you're storing water on the streets, okay, during the storm. Obviously, it impacts anything parked on the street. It also impacts traffic movement at that time. And then the red, and at this small area, this one small area that came out of the model that basically would possibly have some very small over-the-curb flooding. Now 6.56 inches, this is about the 100, this is a little more than the 100-year storm historically. Okay, what we call the 100-year storm and 1% chance. And so what we're seeing is once you get up to that level, you can see that the street flooding and over the curb has changed, and a lot of the street flooding is becoming over the curb impacts. Now we get up to our most pessimistic model that we are going to accept as the numbers within the 95% confidence interval. And again, it starts to show the zones that may be of concern, especially for safety issues as far as moving, fire equipment or hospital equipment, etc., during these big rain events. This is for Hiawatha, and we basically broke it down. These are in millions of gallons. Here, this is the total, and of that total, for the different rainfall amounts, okay, from 3.93 down to 10.1, this is the amount that would be on the street, and this would be the amount that would start to go over the curb and start to impact private property. Okay.
Just a question
Sure.
before you move on. Those are in millions of gallons. You said.
Yes.
Is there any way of translating that into inches of street storage and stuff? Because my understanding is that it's either 6 or 9 is still considered safe, passable for street storage.
What did you, Trish, what was the number you used for the 6 inches?
Okay.
So this is based on a 6-inch curve.
Okay.
Okay. Okay, so when we look at precipitation and percentage of undersized culverts, okay, as we move up, you can see that, around 4 inches, we sort of have a flattening out, and that's basically because when you talk about pipes, everyone thinks about diameter. Okay, you go from, let's say, an 18-inch to a 20-inch. Well, when you have a certain size pipe, diameter means a big circumference. So if you have a certain size pipe, you have a little bit of room in there for surcharging. And so as we get up here, we basically have a series of undersized components going up gradually. But once we sort of reach the real limit of the current system, okay, you have a very steep climb in undersized components through your system. Now, what we did is these are preliminary numbers, but basically you'll see for different precipitation events, and QP means that is basically the peak flow, that is the flow in cubic feet per second per acre. This is the linear feet that would have to be replaced as far as the pipes, and based on some cost analyses we've done, this gives you just a rough idea. This would be sort of the range, the low cost to the high cost replacement for those pipe lengths. Okay, and again, these are just preliminary, but it could just give you an idea of the scale of cost if you were going to try to replace pipes. Now realize replacing pipes, especially in an urban environment, it's very complex because you have all the other utilities you have to deal with, so it's very expensive to get down and replace pipes. And so you're dealing with electric, you're dealing with sewage, you're dealing with power of other kinds, and so the prices can go up very quickly for these. Now, interesting enough, and we didn't expect this, but when we got up to 6.56 inches, okay, you'll see this is basically the existing, and this is with the upsized pipes. We upsized the pipes, and you see how it sort of got the red out of the upper watershed. Okay, that's what it's supposed to do. And so what we did is in that node or that area of the watershed, when we upsized our pipes, you know, we had about 96,000 cubic feet we had to get rid of. The upsizing moved it down, but at that point, we started seeing that the lower watershed started flooding. Okay, because when we upsized, even though we got 0 up above, you see there's a marginal increase in flooding down here in this node, and that has to do with just the way the pipes are configured, and you're also getting very low in the watershed, so there's not much slope, and thus there's much more potential for back flooding in that situation. So we felt that under upsizing pipes beyond the 6.56 inches is not, that's our stop point. Okay, so we had to say, okay, well, after that, what are we going to do with the water? We're going to pay that much money to upsize pipes. How do we deal with the rest of this water that's flooding? So one of the things, and again, I want to thank Lois. This is from a presentation she made last year, so I borrowed it. But one of the ways you can do is deal with on-surface storage or dry basins. And so you're basically finding space and putting a berm, okay, as you can see up there, putting a berm around so that basically you can store water on the surface. And you know, this area already has examples of that in which the city has been very proactive and very progressive in trying to move some of the water off the streets from street storage onto these storage areas. So we looked at the amount of volume of water. This is after. This is from 6.56 above. Okay, that is, we assumed that the first amount would be dealt with pipe upsizing. We looked at how much water we'd have to deal with some of the way. So if we were going to use surface dry basins, okay, what we figured is for these different precipitations amount, starting at 6.56 and going up to 10.1, this is the basically amount of acre feet we would need in storage for the volume that we're talking about. This is in millions of gallons, and these are in acre feet. And an acre foot is an acre 1 foot deep. And if you were going to have surface storage 3 feet deep, you can cut that by a third. So 61 would drop down to around 20. Does that make sense? Yep.
Question. Hey Lois, for the 3 that we have already, how deep or how big are they in acre feet? Just to put it in perspective.
The 3 basins?
Yeah.
I don't know.
Well, I can tell you, about 60 acres is approximately the size of a 18-hole golf course.
That was my point, was, you know, I mean, we don't.
So to give you a scale. So this is just to give you an idea of the estimates of what it would cost to build those. The issue is, where do you find that open space in a developed and built out area?
One other question for Lois might be related to the properties in that part of Minneapolis. It seems like they're all like up, like at least 4 to 6 feet. The houses are higher than the street.
No.
Or what percentage of the houses are like only like a couple feet up above the curb? Because at least in my block, one of the blocks around my house, we're up there at least 6 feet above the curb line before our basement windows even start.
Right. No, it's understandable. Driving around, I've seen that also.
Yeah.
And that's a key point, is that when we do a flood project, we're trying to protect homes from having water in a habitable structure, not necessarily garage. But, so we did a flood project in North Minneapolis, and then we surveyed each property to see where's the lowest window well, or where's the lowest door threshold. So where would water really enter that property, and tried to protect those vulnerable homes. And that's different from it gets to the top of the curb, it tops that, it goes to the sidewalk. And, you know, is that really that hazardous? But where we really start putting a lot of, you know, millions of dollars into a flood project is when homes are being impacted, not just the yard.
Now, this is another project Lois took me to. This is 37, I believe.
Yes.
And this is underground storage, and again, preliminary cost estimates of the volumes that this could handle. These were huge pipe. You actually had up to 12 foot by 18 foot storage containers underneath the ground. These cement and running many hundreds of feet, okay, underneath for underground storage. And we were, again, preliminary cost estimates. If we took our acre feet and how we had to, if we dealt with it that way, it just give you a relative idea of the cost. And what I did over here said how many of those 37th Avenue projects would be paid for by the cost based on what the total cost for that project was. So it just giving you an idea. Again, no one solution is going to solve the problem. All we're doing is trying to give you sort of a relative scale of impact, okay, from different approaches. Realize we're talking about, when we do these numbers, this is the total for a hiawatha, but it doesn't really break it down to, you can break it down to where exactly is that 61 acres should it be based on the nodes or the drainage we saw. Yes?
Going back to Gail's question, one city block, a typical city block, 1 foot deep would be 5 acre feet.
Okay, thank you.
Thanks. So, but that's just amazing that 46 mil, it's almost right up there with putting in a whole new pipe, putting culverts. When you go back to the first scenario of, you know, the 6.56 inch pipe, which came out to, the high end was 54 million.
So, yes?
This is just a question related to modeling, and so a lot of the summary tables that you've shown so far have shown that 6.56 inch storm events, and the numbers you had shown just generally kind of looking at your low, moderate, and high precipitation amounts of that 10-year event. How did you kind of hone in on that? Was that just where, based on all the scenarios you ran?
All the scenarios we ran and looked at the models that we felt were the most justified, and what was within the confidence, you know, the confidence interval, 95% confidence interval. So we chose that. We stopped, again, remember, this is just dealing with the water. We're assuming that the pipes would be enlarged here up to this amount, because at this amount, the system starts flooding other parts of the system. Okay, so we can't enlarge the pipes anymore because we're going to flood the lower part of the watershed. Okay.
Okay, so it's just a value that falls within the confidence
Right.
interval of what was expected.
Now we did look at, we're just starting to look at lid, and looking at, for hiawatha, we're looking at, again, the precipitation. We're looking at, this is peak runoff, and lid, when we say minus 10%, let's just assume that the hiawatha is built out to about 50% impervious. That's actually kind of high in the seclose. Okay. Minus 10% would be taking away 5%, so that 45% of the watershed of connectivity, impervious connectivity, would be, water would be diverted to some kind of lid approach. Okay, so we're just starting to project this. We're going to get much more specific because we've come up with runoff coefficients for different kinds of lid for different densities of housing. Yeah, Lois.
Did you just say that the 6.56 was assuming that the pipes were already upsized?
Yeah,
And
yeah, I
then
think
what's
you
left?
stepped out, but what we
Right.
showed.
And then what's left?
Yeah,
Next
we're
one?
just dealing with what's left.
And I don't know if you said, but we can't just assume that even if the money were available, we could just upsize the pipes because of the impact on the receiving water body.
Right,
Might be detrimental,
right,
and it might impair that water body.
right. Yeah, it's just the system upsizing just stops at that level, just from a flood point of view, not a water quality point of view, but thank you. Is there another question? Okay. So, again, we're looking at how that is impacting runoff, and then we're looking at how that impacts as far as the linear number of feet, basically as far as taking pipes off being oversized or undersized or under capacity, and then we'll be able to translate that to a cost factor. Now, going over to Victoria, again, what's interesting about Victoria is that their system has the piping system, but all the piping systems are going into ponds. And those ponds often have an overflow that's going into a natural wetland system or actually a recreational area next to it, not necessarily a built area because it's not built out that much. And so we basically are looking at when the ponds overtop as well as what's happening on the streets. And what we find is as we build out the watershed there, this is where our build-out analysis were occurring. We found that it really wasn't up to around close to 6 inches that you basically, the blue here is the existing land use and the red is the build-out land use, and basically this is the total flood volume. Is that right around 6 inches you see that there's a difference between the amount of flooding with precipitation. The reason being is there's a lot of resilience that's been built into this system. Those ponds were built with headboards for the 100-year storm. And so you actually have to get up to the historic 100-year storm before you start to see some major issues. And so right around 6 inches, which is the historic, around the 6 inches historic storm, then you start to see where build out, that building in and creating more impervious surface starts to impact the infrastructure there. So this is combining climate change and existing land use at 6.56 inches. You see at that point, okay, we have ponds that basically are starting to overrun, but a lot of times they're flooding out into non-developed areas or onto recreational lands in this area. So this is both climate change with existing land use, okay? So climate change is having an impact, and we basically are doing exactly the same thing we were looking at for Hiawatha, is we're looking at how much of the pipes are surcharged, but we're not getting, the system, it really has to get up to really high numbers before we start to see major impacts because of the resiliency built into that system. So this is precipitation at 10 inches. This is basically climate change, that is the 10 inches, and this is climate change building out. And you can see that you all of a sudden start to have sort of major, this is a recreation area, but you start to have areas that are flooding out. What this is pointing out to is if you basically get up to those rainfalls, you may not want to build out those areas because they may be places where you want to put water and not get into the same sort of constraints that you see in Hiawatha. Okay, and so this is with the build out. And so just to remind you of what those colors are, okay, the green is basically the stormwater ponds are adequate. The yellow is basically the stormwater ponds are less than 10% before they overtop, and then the overtopping, and then this is basically runoff on the Gulf. This is basically going out into recreational areas. This is street flooding, the purple. You can see there's street flooding that's occurring here, but again, it's at a relatively high rainfall amount. It's at the upper 95% confidence interval. So for Victoria, you know, basically they need to really think about how they're going to look at their future build out and what parts of their land they want to consider as set-asides, okay, if these higher rainfall amounts become common as a 10-year storm or a 25-year storm. What we're finding is the historic 100-year storm we're projecting is probably gonna become the 25-year storm. Yep.
So if all the water was being conveyed into the lakes, did you look at what happens to like those homes real close to the lakes?
No,
Okay.
you did not. There's too much watershed and water, groundwater impacting those lake levels. We couldn't model that's beyond the scope of the study, but that's a good question.
Yeah, it was the Hiawatha watershed. You showed the LID impacts between 10%, 30, and 50.
Mhm.
You kind of you kind of went really quickly. Is it possible for us either now or later to go back to that? Because I think it's significant in terms of the cost of that versus the cost of storing it in concrete.
Well, we haven't cost out the lid yet, okay?
I understand,
Okay.
but
I can go back to it right now, as soon as I find the back button. There.
thank you.
Okay, so this is lid. This is minus 10% means minus 10% of the connected impervious. So you're basically unconnecting the impervious surface. So again, hypothetically, if you went from 50% impervious, 10% would mean you send water someplace through a lid process that makes it now a total of 45% impervious. Does that make sense?
Yeah.
I just want to build on Gail's question there, because it's kind of interesting. I hadn't really thought too much about it, but you know, are we getting to a point where we should be looking at ordinary high water levels and see, you know, because we build a lot of our regulations around OHWs. Should we be looking at that?
I think you've got an amazingly complex geology here because you have both a karst topography lens and you have a lake bottom situation which has clays. And so, and I think there's a current study going on, aren't you, with John Gubber, looking at just the lower part of the creek, and it's sort of like, will opening the dam really make a difference in summer flow? Well, not if the geology says the water's going away into a karst lens.
Yeah, on that side, you're right. On the east side, it does get more karsted, but as you go west, it's not karsted anymore. And this world,
No, the home is right next to the lake.
and this house is right next. Just an observation. I hadn't really thought about that.
Well, it's a big, well, I can tell you where we are in New England, we're doing that because almost every lake has a dam control in New England, and those dams are set. And so the question is, are you going to flood downstream in order to maintain the property values on the lakes? It's a big question. I think